Students, I will begin with now. The next thing that we have to talk about is the concept of sequences of real numbers. Sequence of real numbers. What do we mean by a sequence of a real number? I will define sequence of real numbers. Uh, Sequence is nothing but it's just a function whose domain is set up to natural numbers, and that means uh, a sequence is a function f from set of naturals to x, where x can be any set, where x is a non-empty set. And clearly, x cannot be empty because for that you will not define a function. Because if you are defining a function as a set of natural numbers, and natural numbers is a set of naturals in which you have plenty of elements, and if you say that you have a function, then that means every element must have an image in x, and image in x is possible only when x is a non-empty set. That's why we need a non-empty set. So a sequence is nothing but it's just a function from set of whose domain is set of natural numbers. And but usually when you study the sequences, the notation is not kept as a notation of functions. If you how we develop this notation, how we give it a notation. If we take a natural number, then the its image, which is a unique number, then the uh, unique image, which we denote by f of n, and which clearly is an element of x, is denoted. Usually, this is the notation that is kept, denoted by x sub n. So x sub n is some element in the set x, and which is uh, the image of natural number n, and this image is referred to as, and is referred to as the nth term of the sequence. Whatever sequence it is given to you, it is now referred to as the nth term of the sequence. So, in terms of the sequence, so that is the nth term of the sequence, the notation used for denoting a sequence is usually denoted by xn or xn and from 1 to infinity, or we also give a notation just to differentiate so that between a set and a sequence. We use the small brackets xn, or sometimes you may use the range of the range of n and from 1 to infinity. So these are the some of the notations that are usually used to denote a sequence. We will try to stick ourselves to this notation of a sequence. Uh, there are now in this chapter we will be studying the behavior of the sequences, and we will begin with bit by bit telling each thing that we require to establish about the idea of sequences and their importance. Usually, uh, the next thing that is associated with the range sequence, that is the range of a sequence. Since you know the range of a sequence is a function, so range of a sequence is the range of the function. So given a sequence, I will now stick to the notation. Given a sequence xn in some set x, then the set of all terms of distinct terms of the sequence is called the range of this given sequence. So notationally, you need to be very clear what is the range and what is the sequence. Notationally, in terms of the sequence are ordered. You may note that in terms of notationally, the terms of a sequence are placed according to order, placed according to the order of natural numbers. How they are placed according to the naturals, and because as what is the order of natural numbers? You just write one, then you follow two, and similarly, that is, if you have a sequence, you just place the terms of the sequence like this: x1, x2, x3, so on, xn, and continue so on, which has infinitely many terms. Sequence always have infinitely many terms. So just to keep in your mind, you must have that sequence always have infinitely many terms. It has infinitely many terms. Whereas its range may have finitely many terms. Why there is possible? Range is a set, and we do not repeat the elements in a set. And whereas when you write the sequence in the ordering form, maybe you have first term and second term x1 and x2 may be equal, but when you are writing these in this sequence, we have to keep them as a different term. In case of equality, might be equal, but as a term, they are different terms of the sequence. This is the first term, and the other is the second, and the other is the third, and so on. Whereas in case of range, we don't differentiate between terms. We just have to consider as the elements of the set. Whereas the range might be finite as well. Let us see the example. Look at this example. Just define a sequence. Let b be some fixed real number, and for each n in n, let us define the sequence nth term to be equal to b. For every natural number, for every n, the nth term of the sequence I am defining to be b. That means all the terms are same. Then we can see this sequence xn, which I can write as in writing in the order form x1, x2, which is nothing but b. At each place you have a same number. So this is a sequence. This is a sequence, and it is since each term of the sequence is equal, all the terms of the sequence are same. So then, in that case, such a sequence is called a constant sequence. We call it a constant sequence because as a function, this is a constant function. Okay, and so it has infinitely many terms, but the difference is that at each term you have a same number. So this gives rise to its range to be a singleton set, and hence its range is a finite set, and indeed its range has only one element because you don't repeat the element, you have just one element. Look at the other example also, in which you let us consider range to be a bit larger set in terms of enclosure. Let us consider the sequence xn to be equal to -1 to power n. Now, if you write this in expanding the expanded form, You will have first term as minus 1, you will have second term as 1, you will have third term as minus 1, you will have again 1, and you have this alternating sequence of 1 and minus 1. So again, this is a sequence, and here this sequence has a range, it has two elements only, because you have to write only its elements. You don't have to, I cannot write infinitely many times 1 and minus 1, because in case of set, you don't repeat the elements. So it has only two elements. Its range has two elements, whereas the sequence has infinitely many terms. So this has to be kept in mind. Sequence always have infinitely many terms, but the terms may not be distinct. If we compare them, they might be equal. But in case of range, you have all the possibilities. But range cannot be empty. One thing is sure, range cannot be empty. Now let us look at another sequence. Let us look at another sequence. Let us consider this sequence whose nth term. Let me write in a where I consider xn to be 1 upon n. Okay, then we can write this sequence xn in the expanded form. The first term will be 1 and the second term will be 1 by 2. For n, the second term is when you substitute n equals 2. Third term will be 1 by 3 and so on. Okay, these are the, this is a sequence. Now you see this is a sequence, and in this sequence is not a constant sequence because the terms are distinct. One is not equal to 1 by 2, and is similarly no terms of the sequence are same. And what is its range? Then this has the range given to be, its range consists of 1, 1 by 2. Each term of the sequence is now a part of the range because no term is repeating here. And now this range is nothing but it is an infinite set. This is an infinite set. So sequence here can have all the sizes of the range of a sequence. Okay, now how you will encounter the sequences? There are many ways you will encounter the sequences, that you will, there are many ways to get the sequences. One of the way to get a sequence is that you might be given uh, its nth term. Might be given its nth term. Okay, for every n you might be given an nth term, like you can see xn is equal to 1 upon n plus 1, and from this substituting the values of n, you get to all the terms of the sequence. So this gives you the sequence. The first term will be its 1 by 2, then it will be 1 by 3. So in this way, okay. And the other way you get the sequence, maybe you define the sequence starting from its term. For example, 1. For example, you start with 2, you might start with 4, you might start with 6, and after 3 or 4 terms or 5 terms, you might get to know what is the pattern of the sequence. And as in this case, you may see that the first term is 2, x1 is 2, x2 is 4. You can write x2 to be x1 plus 2, and then you see the third term is third term of this sequence is 6, and x6 is 4 plus 2. 3, 4 is second term, you may write. Okay, so one of the way to look at this is this. And similarly, this pattern will give you that the nth term of this sequence is nothing but it is its preceding term, that is n minus 1th term plus 2. So this is something different. Now you have this formula. If you look at this formula for this sequence, which is xn, nth term given by its n minus 1th term plus 2. So this doesn't give you now this formula. This formula is such that it doesn't give you, if you want to find the hundredth term, for example, if you want to find x hundred with this formula, then you will get x hundred and it will give you x 99 plus 2. So again, you to find the hundredth term, you will need to evaluate 99th term, and to evaluate the 99th term, you will have to go back. That means in this case, in this case, uh, to find nth term of the of sequence, whatever sequence this is, sequence, we have to begin from the first term. From the first term, we must begin from the first term. Only then we can reach the hundred term. Directly, we cannot do this. Like in case of whereas if you consider this sequence 1 upon n plus 1, in case of this sequence, whereas in this sequence, I can directly compute whatever term you want to find. In this case, we directly compute any term of the sequence. You just substitute the value of the n, you will get the term of that corresponding term of the sequence. So these are two different ways of defining sequence, and this first one where you have this formula xn is equal to xn minus 1. In this case, you are given x1, then nth term is defined with the help by defining by using these previous terms, and this method is the sequences defined this way are usually known as sequences defined inductively or recursively. So this is a sequence which is defined recursively, or you may call it as inductive. This is something which you can define directly. You just substitute the value of, and then you just define this sequence. So you have these two, and there might be other. We will may if there is, we will get other ways to define sequences, or we will see how sequences can be defined some other way. Okay, let's now talk about some little bit of algebra of sequences and what we can do at the initial stage of the sequences. Let me write this to be algebra of sequences. It's not complete algebra, but just I have to define some kind of binary operations. I have to see since I'm considering, and so I have. But before that, I need to mention note here that we will consider only those sequences for which, let me say, I have considered a sequence to be a function from set of natural numbers to set x, and x can be any set. So now I am particularizing this set x for which x is a subset of real numbers. It can be r or it can be, but and such sequences are usually known as such sequences are called real sequences. Real sequences where the term of the sequence are real numbers. Real sequences are sequences of real numbers, you may also call. So in this chapter, we will be only talking about sequences of real numbers. So first I will define when you will say that the two sequences are equal, when two sequences are equal. I define the equality of sequences. Now suppose you have two sequences, let us consider two sequences. So again, I'm just taking this set volley notation, but I'm not going to prefer this one. I will be using this notation xn and yn be two sequences. Then we say that these two sequences are equal, and saying that the two sequences are equal, the notationally it will be to write in this way, that the sequences are equal if and only if the corresponding real numbers, that are the terms of the sequence, corresponding terms of this sequence are equal. Corresponding terms of the sequence must be equal. Only then we say that the sequences are equal. So the first thing that you might observe from the equality of the sequence is that equal sequences have the same range. If two sequences are equal, equal sequences have the same range, whereas the other way it is not true. Whereas the other way it is not true. Other way it fails, I will say. It fails. Let us look at it. That means when if there are two sequences which have the same range, but that doesn't necessarily imply that the sequences are going to be same. For example, let us consider a sequence, two sequences. I will consider a sequence xn whose nth term is minus 1 to power n, and I will consider another sequence yn whose nth term is minus 1 to power n plus 1, where n ranges from y to n. So this first one sequence is what? This is minus 1, 1, minus 1. This is the pattern of the sequence. And in case of yn, you have the sequence. The first term will be 1, then you will have minus, second term will be minus 1, and then you will have 1, third term, and then you have minus 1, so on. Now you see, you don't get confused that they are the same sequences. You see, the first term of the sequence xn is minus 1, whereas the first term of the sequence yn is 1. So this gives that x1 is not equal to y1. For the equality of sequences, the corresponding terms need to be equal. So they are not equal. Similarly, you may see the second term of the sequence. Look at here, x2 is not equal to y. So in this way, indeed here none of the term of the sequence are going to be equal. So they are not equal sequences. So we can say that this gives us that the two sequences xn and yn, they are unequal sequences. But what about the range? Let us look at the uh, range of this sequence xn. The range of sequence has only two elements. It is either minus 1 or it is 1. And likewise, what is the range of sequence yn? Range of this sequence is also either minus 1 or it is 1. So the range of both the sequences is same, but the sequences are unequal. So this example must bring clarity to you that the sequences might have equal ranges without being equal sequences. That's it. So next, let me define how we are going to add two sequences. I'm going to define addition of sequences. Addition of sequences. Addition of sequences. How we define? I'm going to again define sequence xn plus yn. It gives you a new sequence. That is, you have to add the corresponding terms of the sequence. Okay, this is a sequence. And for example, let us consider, if we consider xn to be some sequence 0, 1, let me consider something much better thing. I will consider minus 1, 1, minus 1. Okay, we will consider the sequences that for which we showed the which we already discussed in the previous slide. 1, minus 1, 1. So Okay, you just add up these sequences. Xn plus yn. What you have to do, you have to add the corresponding term. The first term of the sum of the sequence needs to be the sum of the first term of the both the sequences. First term of the sequence xn is -1 and yn is 1, so it will be 0. And then you look at the second term, and the second term of xn and yn again have the alternate term, so it is 0. So all the terms of this sequence is 0. So it turns out to be a constant sequence. But you can define it doesn't always such as sum is going to be a constant. Similarly, you may define the difference of the sequences. How you may have to define. If you have to take the difference, you just have to take the difference of the corresponding term. So I will write it here that sum and difference can be defined simultaneously. Likewise, we can define the product. We can define product of the sequences. If you have two sequences, you may multiply these two sequences. There are other products also, but we will consider the usual one. You have to just multiply the corresponding sequences and you get the new sequences. We can also define the quotient of the sequences, provided the term that you keep in the numerator needs to be a sequence which has no zero value. Otherwise, nothing will be a, this will be a undefined. Okay, but here y and need to be non-zero quantity. At the same time, you may multiply a sequence by a scalar, but that follows from the product. Multiplying a sequence by a scalar is equivalent to multiplying a sequence by a constant sequence, and so I will write rather prefer if we have a b be a constant, then I can write b dot this sequence xn, and this has to be defined as we just multiply b with each term of the sequence. This is the usual multiplication, and this is just the product of the sequences, and this last one may be referred to as a scalar product, because if you call b to be a scalar, then it's the scalar product, and it is just the product of the sequences. So this is how we will be dealing with such things also in the coming sections of the unit. Yes, sir. So this was all about the basic preliminaries. So let's look at the first thing, that major thing of which we will have good number of properties there. And the first thing that we have to talk about is the boundedness of the sequences. Boundedness of the sequences is matched with the boundedness of the sets. But first, I will give a sequence, just a sound definition of boundedness of a sequence, and you will see that it is same as saying the boundedness of a set. So let us define a sequence. Let us consider a sequence. A sequence xn is, I will give too many. A part is said to be bounded from above. Is said to be bounded from above if there is a real number. There is a real number such that each term of the sequence is less than or equal to that real number. Okay, then we say that the sequence is bounded from above, and then the number, then the real number, which is greater than or equal to every term of the sequence, is called an upper bound of the sequence. It's called an upper bound of the sequence xn. Likewise, we define, likewise, we say that the sequence xn is, okay, I will not likewise, otherwise it will spoil my context. I have written already a sequence is bounded from below if there is a real number, there is a real number uh, such that each term of the sequence is greater than or equal to that real number. Then we say that the sequences are bounded from below, and mm, this real number L, which is smaller than each term of the sequence, is called a lower bound. Is down to be a lower bound of the sequence. So now you have the concept of lower and upper bound for the sequences. And finally, I will say that a sequence, the sequence xn is bounded or is said to be bounded if it is bounded from above, it is bounded from above as well as bounded from below. Bounded from below. Similarly, we have defined the concept of boundedness of the sets. And finally, since now we have defined the idea of, but okay, let me first indeed refer what this boundedness of a sequence has to do with the boundedness of the range of the set sequence. And I will write it as a remark that given a sequence xn is bounded, whether it is bounded from above or bounded from below or bounded from both the sides, is bounded above or below if and only if its range, let me write range of this sequence by this number rxn. I don't think, maybe I will use this notation for the range, but if I find some other better notation, I will prefer to, but at this time, this is range of the sequence. You know what is a range? Range is a set of the terms of the sequence. You just drop the repetition. If this set is bounded, sequence will be bounded from above. If the range is bounded from above, sequence will be bounded from below if the range set is bounded from below. It is very easy to verify. It's very easy to see. It follows, indeed, it follows from the definition. And now you have the concept of boundedness of a sequence related is equivalent to the boundedness of its range. So now we define its supremum and infimum as well, and all the properties, all the results that are true for supremum and infimum are what the supremum is also known as least upper bound, and this infimum is also known as greatest lower bound. All the results hold for the supremum and infimum of sequences also. So we define supremum of the sequence xn to be the supremum of its range set. We define supremum if its range set, and its infimum is defined as infimum of its range set. Indeed, this thing is nothing but this is actually this will come out again to be supremum will be and the least upper bound of least upper bound. If you find all the upper bounds of the sequence, then it will be the least upper bound, and this infimum is nothing but it is just the greatest lower bound of all the lower bounds of the given sequence xn. Greatest lower bound. Okay, so the concept is true already there. For example, and let me state this for the record that a real number u is supremum of some sequence xn if and only if first thing u needs to be is an upper bound. U is an upper bound of U is an upper bound of sequence xn And the second thing is that for whatsoever small number you take, uh, there exists there exists some term of the sequence xn such that that term of the sequence xn exceeds becomes strictly larger than u minus epsilon. That means if you make this least upper bound little bit of smaller, if you then it no more remains a upper bound. Some terms of the sequence will escape out of this number. And likewise, uh, a real number, likewise a real number L is infimum of a given sequence, infimum of a given sequence xn, if and only if we have these two things. The first, that L a lower bound is a lower bound for the given sequence xn, and second, and the last thing that will make it complete the hypothesis of this theorem is that if you add up something, if you add up with some epsilon for every epsilon bigger than zero, there is a term of the sequence such that this term of the sequence will become smaller than L plus epsilon. Okay, this is the same result that holds for the definition of supremum and infimum of a set. Uh, Another interesting property, that another equivalent definition of boundedness of a sequence can be interpreted through modulus function, and that can be put as an observation and may be recorded as a result. And it states that a sequence xn of real numbers, usually we have a sequence of now real numbers only, is bounded sequence if and only if there is a positive real number, such that the modulus of the sequence, the terms of the each term of the sequence is strictly less than m for all n in n. So this is something. Let's quickly look at its proof. How it's going to help us. First, let me change the color. I'm just writing here red on that. Let me use. First, suppose that uh, sequence xn is a bounded sequence. Let us suppose that it is a bounded sequence. So what it means then, it is a bounded sequence, it is a bounded from above, so it will have a upper bound, and it is bounded from below as well, so it will have a lower bound. So I will go like this. Then there is a lower bound, there is a lower bound L, and you will have upper bound, let it be U in R, such that U being a lower upper bound means it is greater than or equal to uh, it is greater than or equal from every term of the sequence, and again L being a lower bound means it is less than or equal to L for every lower bound of the for every term of the sequence. You have this thing. So now let us choose some number m prime to be maximum of modulus of L and modulus of U. So I'm proving this theorem with the strict inequality here, but it can be proved for less than or equal to also. If you have to prove it for less than or equal to, then this M prime will go. But since I have used it strict, so I will go for strict inequality. So look at this thing now. Let's look at what this M prime. This M prime is maximum of mod of L and mod of mu. So now look at this thing. Since this M prime is maximum, so mod of L. Okay, let me. So mod of L has to be less than or equal to M prime. What it implies? It implies by the definition of the modulus, you will have minus of M prime less than or equal to L, and L is less than or equal to M. And also you have this mod of mu, mod of u, which is the upper bound. This is also less than or equal to M prime because M prime is maximum up to L and modulus of L and modulus of u. So this also implies that minus M is less than or equal to u, and this is less than or equal to M. So we have these two inequalities. For the case of L, I will use this part of the inequality, and for u, I have to use this last part of the inequality. So what you have, we have this thing, L being the lower bound of the sequence. Every term of the sequence is less greater than or equal to L, and what, but at the same time have L to be greater than or equal to M prime. Okay, now xn is also term of the sequence is also less than or equal to u being an upper bound, but the second half of this inequality, boxed in yellow, says that u is less than or equal to M. So dropping out this L and u, what inequality I reach? I reach at this inequality where I have M prime being less than or equal to xn. This is less than or equal to M for all n. So if I put M equals to this M prime plus 1, then clearly this inequality implies that minus of uh, M prime plus 1, which is actually equal to M minus M, this gives us to be strictly less than uh, minus of M prime, and it is less than or equal to xn, and which is further less than or equal to M prime, and M prime is strictly less than M prime plus 1, which is equal to M, and so what we get this thing minus M strictly less than xn, and this is strictly smaller than M for every term of the sequence. And this last inequality is nothing but this last inequality says that modulus of the term of the sequence xn is less than is strictly less than M. So this is the direct part. The other part follows directly in case of the other way. Suppose you have a sequence which has this inequality. Suppose xn is a sequence such that modulus of each term of the sequence is smaller than M, then this you just apply the definition of the modulus of the term xn, which will imply minus M less than xn and is less than M, and this is true for every n. So now what you get from here that this inequality implies that this is lower bound of this sequence, and since it is a lower bound, so that you conclude that sequence is bounded from below, and the second half of the inequality gives you this half of the inequality gives you that this M is upper bound. So this sequence has lower bound as well as upper bound, hence this is a bounded sequence, as the given sequence is bounded. So this is another equivalent. So let me conclude with something very interesting. So what do you have? I have the sequence. Suppose I have a bounded sequence. Then this result says that you will have a natural number. You will have a real number M, positive M. And if you have a positive M, So minus of, I have 0 here, I have minus of m to this side and suppose m here. Then it says, what this says, that this sequence being less than m means minus m less than xn is less than m, and this happens if and only if this term of the sequence lies inside this open interval. That means whenever this sequence is bounded, then this sequence lies in some interval. Yeah, that means now in this case, all the elements of the sequence are lying between this interval. How they are spread here, that is the different situation, how they might have spread here. But the one thing is sure, that no element of this sequence lies to the left of minus m and to the right of m. Every term of the sequence is captured between this interval. And what is this interval? If you observe that you have equal distance to the left and right of the zero, so this is a neighborhood of, this interval is a neighborhood of zero, and indeed it is a delta neighborhood, but you have delta m, m here, delta equals to m, so I can write this is a neighborhood, and this neighborhood, if notationally it has to be it is n m 0. So in that case, you can say that each term of the sequence lies in some neighborhood of 0, some neighborhood of 0, some delta neighborhood of 0. So equivalently, we can keep this also in our record, that a sequence xn is a bounded sequence, is a bounded sequence if and only if there exists a delta neighborhood, say n delta of 0, such that each term of the sequence lies in that delta neighborhood. That this delta neighborhood contains all the terms of the sequence. So this is equivalent, and this is the definition of the boundedness of sequence in terms of the neighborhood, and it directly follows from the previous result. Indeed, previous result is equivalent to saying this. Now let us finish this with an example of a bounded sequence, and let me consider this example that we have been considering frequently, and look at this sequence 1 by n, 1 by n, and I have 1 by 2, 1 by 3, so on. So see, note that for each n, you see the term, nth term, this term is always greater than 0. So each term of the sequence is greater than 0. So what it implies? Uh, it implies that 0 is a lower bound, is a lower bound for this sequence 1 by n. So it is bounded from below. Also note that for each term, this number 1 by n is less than or equal to 1. So this gives that 1 is an upper bound for this sequence. This is an upper bound for this sequence. Hence, it proves that this sequence is a bounded sequence. It has upper bound as well as it has lower bound. Is a bounded sequence. Whereas if you look at, let me also mention another example, that a constant sequence is always a bounded sequence. Constant sequence, that is, let me consider this b, so is a bounded sequence. I don't need to find its lower bound or its uh, upper bound. Why? Because because its range set is a singleton, because its range, which is equal to singleton set, is a bounded set. You know that singletons are finite sets are always bounded sets. Hence, the sequence is bounded. And let me consider an example of a sequence which is unbounded. Let us look at this sequence uh, 2n. This is sequence of even integers. You see, you have first term 2, you have 4, you have 6, you have 8, and this sequence is bounded from below, but is not bounded. And a sequence which is not bounded is usually referred to as an unbounded sequence. But it is not bounded from above. How are you going to establish that it is not bounded from above? Suppose, on the contrary, that it is bounded from above, then what happens? Suppose, on the contrary that it is bounded from above, that means it will have a upper bound. Suppose, on the contrary, that there is a real number u such that each term of this sequence, what is each term? 2n is less than or equal to u for all natural numbers. So what it implies then? It implies that n is less than or equal to u upon 2 for all n in n. That means that this implies that this u upon 2 is the upper bound for the set of natural numbers. That is, set of natural numbers is a bounded set, but we very well know that this is not the case. So it gives us a contradiction, and hence this proves that this is a not a bounded sequence. So we end up here.